So now I'll start live streaming.
どうやって消せばいいんだろう。あ、消えた。あら。ビデオ送って。はい、さん、can
Yes, I can hear you.
あれ何これこれは私ではないから、どっちかな。
So please speak, France. So your session there.
Okay, so let's start after the first is
Maybe Kato-san need to mute. So I will make mute Kato-san. Huh? So please start. What happened? Please start.
あれ聞こえてない
Okay, okay. Now, okay. You can speak.
This talk is based on the two papers. One is co-authored with Fragnon, Professor Rigal, and Paz. And another paper is also François Rigal and his student, Miyamoto-san. Yes. Today's talk is related to these three topics. One is distributed computing. This is a kind of theoretical computer, one topic of theoretical computer science. Many computer collaboratively to solve some task. Another two, one is all of you know quantum computing. Another is the computational complexity. This is the study to measure the time complexity or space complexity and so on. First, I speak about this intersection, this topic, distributed verification. As François talked in the morning, I talk about NP. NP has three interpretations. One is based on non-deterministic tuning machine. Its extended class is PP and SHAP-P. Second is a logical structure. It's a related class is polynomial time hierarchy. Third is
Sorry. I cannot watch the Nishimura-san's face. So could you open the video?
Video.
Maybe you are using the 509. So 509 does not show the video. Now video is closed. 509. You are using 509 or maybe 509. Yeah, okay. But I cannot see your face. Okay.
これは、これはカメラオンにしましたけど。でもなんか隠れてるね。まあいいか。Okay. Anyway, today, this talk uses third interpretation called proof system. でもなんか、聞こえにくいかなと思って。NP as proof system is consist of two party, prover and verifier. Prover has unlimited power, while verifier has a polynomial time computation. Prover sends some string called certificate or proof. And the problem, yes, no problem, A is in NP, if and only if there is polynomial time algorithm. That satisfies two property. One is completeness. If X is yes instance, then there exists certificate verifier accept. Another important property is soundness. If X is no instance, then any certificate-like string verifier reject. This is the NP. Now, distributed certification case, verifier consists of network. So now verifier, there are several verifiers. This distributed pairing answer protocol has been studied in the distributed computing community since 2005, I think. In this case, the input is graph itself. It's the verifier's connectivity representation, and also the string of each node. Some node has such an input. And prover send the message to each node. Certification has two phases. First phase is prover phase. Prover send certificate to each node. After that, verification phase. Now each node exchanges a message with its neighbors, only neighbors. This after this process, we have similar property, completeness and soundness. In this case, some witness exist such that all node accept. Important point is that now the verifier are multiple. Such a multiple verifier must accept, all of verifier must accept. If, on the other hand, in no case, any for any witness like reject. This is the definition of distributed certification. Now we move complexity parameter. Here we consider two kinds of complexity parameter. One is certificate size. This is length of the message which the prover sent to each node. Another important complexity parameter is the message size. This is the length of messages sent on each edge in the verification phase. The example is the famous NP problem called three-colorability. This is the network is three-colorable or not. we want to check. But the network, the node of network cannot freely communicate each other. So how do we check the network is really three-colorable or not? In fact, this is very simple. As you can see this figure, this network can be three-colorable. So prover send corresponding color. For example, the most orange color part to to 1, and green color to 2, and blue color is 3. Then the every node can easily check by exchanging the message, and neighbor's color are different. Now this complexity certificate size is clearly order 1, and the message size also order 1. So this is a very efficient proof system. Now we move to today's topic, quantum distributed certification. QMA is the quantum NP, as talked by François. This is just two part is change. First change is the proof. Now proof is not classical string, but quantum string, quantum state. And verifier's algorithm is now not classical algorithm, but quantum algorithm. And also the completeness is if X is yes instance, then exists some quantum witness such that we accept with high probability. No case, if X is in no instance, then for any witness-like state, the verifier reject high probability. Now we consider the distributed quantum memory answer introduced by Rainol et al. This case now similar to distributed memory answer, but the now message from prover is quantum, and also the exchanging message among nodes of network are also quantum. Now, natural question is, which problem are efficient for DQMA protocol? Here, DQMA is acronym of distributed quantum memory answer protocol. Such a problem we found the simple problem called equality. Now, this problem is very simple. Network subset of network node have input X, Y, Z, etc. Such a node is called terminal. The question is, all the input are equal or not. Really, this problem is no constant round protocol. If any prover does not help, because simply if this 3 node is very far in the network, only one round communication, they are they are not communicate each other. So we need to help of prover like NP-like problem. Now we have very trivial protocol for equality. The protocol is like this. First, prover send X, then all data are X. So terminal in this figure, terminal has only three party, but prover send same data to another node. Now, in the verification case phase, each node check it is same as neighbors one by just exchanging the message. Really, this satisfies completeness. Also, soundness hold, because if, for example, the one node has different input, then there is always have some different string. So some node reject with certainty, like this black node, black line. But unfortunately, this trivial protocol is communication inefficient because prover send X itself, data itself. So if length of data is n, the length of the proof must be n. This is inefficient. Now we move to our result of equality. First, we can show the classical lower bound for EQ. Any DMA protocol requires omega n bit certificate if error probability is reasonably small. So previous trivial protocol is some kind of optimum. But quantum case is different. There is a DQMA protocol for equality of replicate data with log n plus r times graph size qubit certificate and message. So improve exponentially in n the length of data. Of course, this complexity has T and R. Both depend on the network size. So this result is meaningful when T and R are typically is smaller than N. It's a typical case, I think. Now, I show the protocol shortly. Our protocol is relatively simple. It's an extension of the SMP protocol of a quantum SMP protocol for equation by Berman-Cleve with Butler's-Wolf. Now, we consider the network line case. Then the prover send certificate HX. It's a quantum fingerprint of X to each of intermediate node. Here, fingerprint is almost orthogonal to another fingerprint. It means that HX is orthogonal, almost orthogonal to HY if X not equal Y. Also, the length of HX is order log n. On the other hand, both ends have input, so they create a fingerprint by themselves. Now, verification phase. Each node Vj choose random bit Bj uniformly. If Bj equals 0, then Vj send the fingerprint from prover to the right neighbor. Otherwise, keep it by self. If some node has two fingerprints, for example, in this figure, V3 has two fingerprints. One is from V2. One is keep himself by the result of coin. This case, V3 does subtest to check the two fingerprint is close or not. If someone reject after the subtest, the protocol reject. Otherwise, accept. This is the protocol for line case. Clearly, completeness hold because X equal Y, then subtest always pass. But if X not equal Y, then HX is almost orthogonal HY. So intuitively, some node reject by subtest. Of course, the malicious mirroring send very strange quantum state. So the analysis is not so easy, but I skip such a detail. Once we get the line case, general glass is reduced to line case because we consider the spanning tree of the network, which is sent from prover, and such a spanning tree can be checked by network locally, which is known result. So now once we get the spanning tree, we can run the protocol online simultaneously. That's for general case. Now, natural question is what other problem can be solved efficiently, verified efficiently? We obtain two problems. One is set equality, and another is state generation. Now, set equality is defined as follows for two-party case. Each party has two lists of elements in the finite set universe U. Output is yes, if and only if the set A, which is AJ, AIJ, J is in 1 or 2, and I is in 1 to L, also B is similar, are same as multiset. This is the example. This case, A is 1, 2, 2, 4, 5. A2 is 5, 3, 1, 1, 4. B1 is 4, 1, 3, 1, 1. And B2 is 4, 2, 2, 5, 5. Now A is 3, 1, and 2, 2, and 1, 3, and 2, 4, and 2, 5. Also, large B is same. So the this instance is yes, yes instance. It's a kind of the histogram. So A1 is the one, the height is 1, and 2, height is 2, 3 is height is 0. If like that, if we consider such a consideration, the question is the sum of histogram of A equal sum of histogram of B. This is the intuitive interpretation of this problem. Now we simply extend to this problem to more than two-party on graph. This is considered by Nagoya et al. In distributed computing setting. This is input is graph G, and each node has two lists of L elements in finite set. The question is the same. The sum of histogram about A equal sum of histogram about B. For this problem, we get to the efficient DKNL protocol also. Certificate size and the message size is a little bit complicated, but the important point is the length of list L and size of universe U is logarithmic. So, and also we get the lower bound of classical case. Comparing these two results, the quantum case improve exponentially in L, parameter L and parameter U, size of U, size of universe. Now we move to state generation. Recently, quantum problem is a lot of attention, called state synthesis and unitary synthesis. So the point is that considering computational complexity of generating quantum state or quantum operation. Traditional study is the computational complex theorists consider the classical problem. But recently, some researchers consider quantum problem. Our second problem is regarded as such a quantum problem. We call this problem SGDI, state generation on distributed input. This problem is like this. We consider this problem online. Now, left node V0 has classical description of n-qubit state psi. This is not unknown state. And Vj has unitary transformation Uj. The goal is generate R2 to U1 psi at VR. So VR must output such a state. Of course, round extent way. Of course, this is impossible one round. Now, we consider again with help of prover. To consider such a case, we certify the property of distributed certification. Yes case, all node accept. No case, some node reject. But this property is for yes/no problem. This problem is not yes/no problem. So completeness and soundness is slightly changed as follows. First, completeness, there is some state witness or node accept, and VR output the desired state. On the other hand, soundness is a little bit different. It means if all node accept with reasonable probability, then output of right node satisfy the closeness. VR must output a state that close to ideal state. That's a soundness condition of state generation case. For this problem, we have the following result. There is a DQMA protocol for SDGI. this parameter is reasonably well, I believe. This proof idea of is relatively simple, at least intuitively. Just incorporate the FLNP protocol into the idea by Morimae Takeuchi Hayashi for verification of graph state. So for this problem, FLNP-like test can be considered also. For example, Martin send U1 psi to V1, U2 U1 psi to V2, etc. And also V1, V2, etc. Flip the coin and send. For example, V1 send U1 psi to V2. Then V2 apply U2 such a state, and U2 if keep his proof, then subtest applied. So we consider similar test. Now we incorporate such a similar test to Morimae Takeuchi Hayashi framework. So we have many such a state proof from Melody. So M plus K plus 1 copy. And each node permute for keeping symmetry and discard M copy. And K copy must check to FLNP test, and remaining one is output. This similar analysis to Morimae Takeuchi Hayashi, we can prove the theorem one. Now, another improvement. The QMA protocol has two phases. Another question is, can we replace the quantum communication of verification phase into classical communication? In the figure, the quantum message is replaced classical message. Is it possible? Such a verification by local operation and classical communication in the verification case. Then we call such a protocol LOCC DQMA protocol. So question is, DQMA protocol can be converted to LOCC DQMA protocol. The answer is yes. The theorem is a little bit complicated, but any DQMA protocol can be converted to LOCC DQMA. Using this result, we can convert for EQ protocol. So there is LOCC DQMA protocol for equality, similar advantage compared to classical case. Of course, graph parameter complexity are a little bit large, but now our focus is the length of string parameter. this proof idea also borrowed from verification result. Idea is very simple. Just replace the quantum communication is verification phase into classical communication by sharing EPR pair sent from prover with the original witness. Such a EPR pair is sent from prover, so prover may be malicious. So to keep the soundness, we use the Zhu-Hayashi result for verification of a EPR pair in adversarial scenario. Now I finished my talk. Thank you very much.
Thank you very much. Any questions on site or online? Okay, so I have one question. So for the first part of your talk, for the equality function, if we have quantum witness, then you can do it with very small complexity. If it is classical witness, you need very long witness. But what happens if you consider a setting like distributed QCMA?
Distributed QCMA.
So the witness will be classical, but you allow quantum communication for checking. Is there some... My intuition is that this will not help. It will still require very, very long witnesses.
Yes.
But can we prove that?
Maybe our lower bound argument is based on the classicality of the proof, I think. So using the counting argument. So after verification phase is quantum or classical is no problem. So my answer is not sure, but as far as I remember, QCMA case is still similar to classical case.
Okay, thank you. Yes, it makes sense. Indeed, if I remember well, indeed, it's the fact that we will have two inputs with different inputs receiving the same witness, and then we cannot give the same output. Yes, I see. Yeah, thank you. Thank you. Any questions? Any question online?
Sorry, I have a small question. So you use my older results for some verification. So could you explain how did you apply that kind of verification method? What's problem? Could you explain that problem again? Your problem.
So this second result is very simple. So this result is just the verification stage. At the verification stage, we want to quantum communication, replace quantum communication into classical communication. So we just consider the quantum teleportation. So the network keep EPR pair. Then using EPR pair and classical communication, we can implement quantum communication by quantum teleportation. But the network originally does not have a share EPR pair. So prover send EPR pair. But prover is malicious. So your result is needed.
So you use my result twice. So this is the second result.
Yes.
This one is somehow verification of general quantum state. So we can use that result even though we don't have the locality condition. So now you send the quantum state. So then prover have a whole quantum system. So there is no LOCC restriction. Okay?
Yeah, prover originally send any state, the proof original protocol, prover send some state, but now important is additional EPR pairs. So to keep the shared EPR pair among nodes in the network, prover kindly help by sending EPR pair. Then network can use teleportation. But if prover is not honest but malicious, then
Is not honest but malicious.
prover send any illegal state. Unfortunately, your result, any the state is EPR pair or not, can be checked in adversary scenario.
So you want to consider that kind of adversarial scenario. So this is not IID. Okay, please proceed. So maybe I need to consider again by myself.
Okay, any other questions? If not, let's thank Harumichi again.
Thank you.
Okay, so we have maybe a question on the next speaker, so you can come in and connect your computer, and we'll start in 3 minutes as scheduled. We have a 3-minute break.
Hi everyone. Thank you for inviting me, and it's my honor to give a talk about my recent research. My topic is quantum lower bound by sample to carry lifting, and this is a joint work with Zhicheng Jiang from University of Technology Sydney. And this work is about maybe an arguably new proof technique for quantum carry lower bound from the information theory perspective. Okay, now our story begins with the well-known quantum algorithms. As we all know, two of the most well-known types of quantum algorithms. One is quantum algorithms with query access, and the other is the quantum algorithms with sample access. For query access, we usually mean given a quantum unitary oracle U, and we want to learn certain properties of U. And the problem is to ask how many queries to U are required to learn this property. And this is also known as the quantum query complexity. There are some examples, the well-known ones, quantum search and phase estimation and amplitude estimation, solving systems of linear equations. And these are very well known. And we here also consider another type of quantum algorithms with sample access, very similar to the case of quantum oracles. Here, we are given a mixed quantum state, rho, and we want to learn certain properties of rho. And the problem is to ask how many samples of rho are required to learn this property. There are also examples, including quantum state tomography and quantum spectrum testing, quantum state certification. As we know, in this type of algorithms, we only use quantum states, but not oracles. And our question is there any relationship between quantum query complexity and the quantum sample complexity? One is that the algorithms only use quantum oracles, and the other only uses quantum samples. And in this talk, we'll review a novel relationship between quantum query complexity and quantum sample complexity regarding quantum state testing problems. Well, now we'll first introduce the notion of quantum state testing problem. A quantum state testing problem P is a promise problem, and it is asked to determine whether a given quantum state rho is an yes instance or a no instance. Promise that it is in either case. And this type of promise problem is well studied, and the most illustrative example is the quantum state discrimination. And here we denote as DIS rho sigma. And this problem is to determine whether a quantum state is rho or sigma. And given that the quantum state must be in either case. And this problem is known as quantum state discrimination and was studied maybe 2 decades ago in physics journals. Another example is the mixedness testing problem. That is to determine whether a quantum state is maximally mixed or is far from being maximally mixed. And these are the examples. Now we are defining the quantum sample complexity of P, denoted by SP. It is measured by the minimum number of independent samples of rho for solving P with success probability at least 2/3. Also, we here define the notion of quantum query complexity of P, denoted by Q diamond P, is defined as the minimum number of queries to the block encoding of rho for solving P with success probability at least 2/3. And here, a unitary U is a block encoding of rho if rho is in the upper left corner of the matrix representation of U. And here we study this type of query complexity. And now we are able to state the main result of quantum sample to query lifting. It is very simple. Let P be any quantum state testing problem. Then the query complexity of P is lower bounded by the square root of the sample complexity of P. That is if we have sample lower bound of P, the quantum state testing problem, then the square root of SP is a lower bound of the query complexity for certain problem. And what does it mean? Our lifting theorem reveals a novel connection between quantum state testing and unitary property testing. So for SP, it's about quantum state testing, and for Q diamond P, it's about unitary property testing, that is to test certain property of unitaries. It provides an arguably new method for proving quantum query lower bounds. And this is done by reducing from quantum state testing. We can systematically derive quantum query lower bounds using corresponding sample lower bounds from quantum information theory. Using this lifting theorem, we are able to systematically derive a lot of quantum query lower bounds for several problems, including state discrimination, rank testing, mixedness testing, uniformity testing. And this is about testing for some properties of unitary. And some more general cases, problems, including Gibbs sampling, entanglement entropy, Hamiltonian simulation, phase estimation, and amplitude estimation. So here we give an illustrative example to show how the lifting theorem can be used to prove quantum query lower bounds. And this example we choose is quantum Gibbs sampling. Quantum Gibbs sampling is a task to prepare the Gibbs state proportional to e to the minus beta h of a Hamiltonian h at inverse temperature beta. And this problem is very popular in quantum SDP solvers. And the state-of-the-art quantum Gibbs sampler is due to the paper of quantum singular value transformation and with query complexity O beta. However, it is not known any lower bound for this problem. Using our lifting theorem, we are able to show an optimal query lower bound for quantum Gibbs sampling. And this is our corollary of the lifting theorem. The corollary states that any quantum Gibbs sampler has query complexity omega beta. And the proof is surprisingly simple, given the lifting theorem. Now let us consider the quantum Gibbs sampling, consider the quantum state discrimination problem between between rho plus and rho minus. Here, rho plus and rho minus are quantum states and chosen as above, and their infidelity is gamma about 1 over beta square. And then suppose that we have a quantum Gibbs sampler with query complexity Q. The Gibbs state of, and note that rho plus and rho sigma, rho plus and rho minus are Hamiltonian. They can be considered as Hamiltonian because they are emission matrix. So the Gibbs state of rho plus at inverse temperature beta is proportional to the state e to the plus or minus 1, blah, blah. And the two quantum states can be easily distinguished by measuring it in the computational basis. So that is, quantum Gibbs sampler can be used to distinguish rho plus and rho minus. So the query complexity Q is lower bounded by the query complexity of quantum state discrimination between rho plus and rho minus. And by the lifting theorem, it is lower bounded by the square root of the sample complexity. And it is known that the sample complexity is lower bounded by 1 over gamma. And by simple calculation, it shows that it's omega beta. And we also have other new results and new proofs of some known results, but for the time limit, we skip other applications. And then we talk about the optimality of the lifting. We show that the lifting is optimal by giving an explicit problem. This also quantum state discrimination, meaning that lifting is tight and saturated by the quantum state discrimination problem. And because of the optimality and the lifting, we can have a figure as shown here. The bottom case is our SQ diamond relation for quantum state testing, and the above is about the quantum query complexity of Boolean functions, and as we can compare. And for the above one, the results are well known. And for Boolean function f, we know that df is the deterministic query complexity of f, and qf is the quantum query complexity of f. And we know that df is always upper bounded by qf to the 4. And we also know that there is a Boolean function f such that df is almost qf to the 4. And for our lifting theorem, we show a relationship between the sample complexity and the query complexity Q diamond. It's called SP and the Q diamond P. For the lifting theorem, we show that SP is always upper bounded by the Q diamond P to the 2. And the optimality show that there exists a quantum state testing problem P such that SP is lower bounded by Q diamond P to the 2. So this figure shows some similarity between Boolean function and quantum state testing. Now we give some open questions about the result. One small question is that our quantum query lower bound for Gibbs sampling holds when the oracle is a block encoding of the Hamiltonian. And also the state of the art quantum Gibbs sampler is also defined in this input model. And can we prove a more stronger lower bound for when given query access to the classical data of Hamiltonian, just as the HHL algorithm, they usually assume query access to classical data. But the lifting theorem can only derive a lower bound for the block encoding query model, but cannot produce a lower bound for the query access to classical data model. And another philosophical question is that, is there a classical analog of the quantum sample to query lifting theorem? If it exists, we believe it could be a new tool for proving classical lower bounds. However, the difficulty is that it is not clear how to interpret block encode in classical computing. How to block encode, that is how to block encode classical information in classical logic gates. So far, I have no idea about how to interpret block encoder in classical sense. And that's all of the talk. Thank you very much for your listening.
Thank you very much. Any questions?
So I have a question. So I have a question about the lifting. So you are using the lift?
Yeah. I'm here. Yeah.
Yes, but I could not find the lifting. Lifting is somehow converting the quantum state to the some query unitary. This is correct?
Excuse me, what can you?
Originally, you are considering the state discrimination.
Yeah.
But after you applying a lifting, you can consider query complexity, discrimination of queries, I think.
Yeah.
So what is the correspondence between the that quantum states and queries? Maybe that kind of relation given by that kind of lifting.
Yeah. Yeah, I think it's the interesting part is that if we only have sample complexity, we can give a lower bound to for query complexity.
No. I'm asking what is the relationship, because this is originally different problem. So sample complexity is complexity for state discrimination, problem for state. But now you are considering query. So query is a different topic.
I'm sorry. I don't understand completely.
So you are originally considering the sample complexity. This one is state discrimination, but that kind of problem is related to the so what kind of state you are considering? So you did not give the definition of sample complexity. You are considering the two same sequence of states.
Do you ask the definition of sample complexity?
Yes, first. You please answer this question.
For the sample complexity, that is, we give sample access to row, and we can have identical copies of row, as many as you want.
But in that case, okay. In that case, the problem depends on set P yes and P no. And so you are considering complexity. Complexity means that sample complexity means that you need to repeat several things, not only one copy. You are considering two copy or n copy case?
Copies.
Hmm?
You can have copies.
So, and there is another problem. So, first row and second row is the same, or only they belong to the same subset. So, P, yes, is not a single element. You have a several elements in P, yes, and you are considering the n-tensor product of the same states in P, yes, or P, no.
If for many independent copies, we assume that we are given row tensor K, and K is the sample, the number.
Row tensor K, okay, I understand. Okay, so then now you can define the problem.
Yeah. And then define the problem, we given row tensor K as input.
But
And K,
sometimes these are somehow the state sometimes move or fixed. Sometimes that set moved somehow. Usually you fix that error 2/3. So in that case, maybe this one is somehow but this is only constant. So maybe you are considering some parameter about the set P yes or P no, I think. Okay.
you mean you mentioned that we need to give some parameters with respect to P?
Yes, so yeah, I think so. Otherwise, you cannot formulate that problem.
Here, P is very general, and in our lifting theorem, there is no limitations or constraints.
Okay, I understand. Okay, so then please back. And also again, please back previous slide. So now you consider this is lifting. So unitary is U, but block encoding row, this is truly unitary.
Yeah. Do you mean the quantum query complexity defined here?
Yes.
Yeah.
Row is density matrix, I think.
This is that you consider that we are given unitary oracles U, and the upper left corner of U is row, and we want to learn certain properties of U. Certain properties of row according using queries to U.
No, I cannot understand. Row is not density. What is row? So in the case of query complexity, you consider row, but that row is different from sample complexity, I think. Or in the case of sample complexity, row is density matrix. But in the case of query complexity, row is density matrix or not?
So sorry, I didn't see the difference.
Because at least in the case of sample complexity, rho means that density matrix, okay? Rho is density matrix. No? What is rho in the case of sample complexity?
In the case of sample complexity, where does it wrong?
Rho, what is rho? What is rho? Rho. Maybe in the case of rho. What is rho?
I'm sorry.
My English is so bad. So rho. RHO. Rho is density matrix. Mathematics.
I'm sorry.
Yeah, I think rho is a density matrix. So you put the density matrix.
Of course, rho is density matrix, but in the case of query complexity, what is rho? Also density matrix.
Same, which is encoded as a block of a unitary. So you have access to the unitary. And one part of the unitary, the big matrix, correspond to the density matrix rho.
I'm very confused. U is unitary, but in this equation, a part of U is given as rho, but that rho is density matrix.
Yeah, rho is a density matrix.
Huh? But this is quite very special unitary, and usually general unitary does not return in this form. And where unitary has that form?
You are asking why unitary has that form?
Yes. But usually unitary cannot be written in this form.
Just as the promise problem, we promise that U has this form. So this is encoded in the promise problem itself. Are you asking about this?
So you are considering very special query. General query cannot be written in this form. Very special unitary.
Yeah. This is a very special unitary.
So this is lifting. So originally you consider sample complexity by using rho, and that sample complexity problem can be converted to query complexity by using this correspondence. This is correct?
This is because if you want to encode the quantum state testing problem in the scenario of unitary cases, there are incountably many possible cases to encode this problem. So this is only one possible encoding.
No. I am asking the definition of lifting. This slide gives the definition of lifting, I think.
So sorry, I didn't understand.
No, because you suddenly give the lifting, but you did not give the definition of lifting. Lifting is somehow correspondence between the somehow state complexity and query complexity. So you need to make a correspondence between the sample complexity and query complexity. I think previous slide you give that correspondence.
Yeah, this is. I think this is really a correspond.
No. This slide does not give that correspondence. This gives the only result, not definition.
I think the definition comes from the previous slide.
Previous slide. So then I think the title of this slide is very misleading. You give the lifting in this slide, not the next slide.
Can you say page 11 or page 12?
Yes, in page 11 you give the definition of lifting, and in In 12, you give that result, not definition. Definition is given in the 11.
11, okay.
So you need, the title is very misleading. So the title of 11 should be lifting. Otherwise, nobody can understand this problem. The title of page 11 is very misleading.
You mean misleading in the definition of what?
Because in page 11, you give the definition of lifting.
There
That
are,
definition, you give the result in page 12.
in page 12, and
Yes,
then
this is only result, not the definition.
the definition is in 11, so where it
Yes, so you need to explain the definition of lifting given in this page.
so do you mean the definition is misleading, or in what sense wrong?
At least you should explain the definition given in this page 11, not 12.
Do you mean the first definition of quantum state testing problem, or the second definition of quantum sample complexity, or the third definition of quantum query complexity?
No, I'm mentioning the lifting, the definition of lifting.
Or the definition of lifting?
Yes, lifting gives us some correspondence between the sample complexity and query complexity.
Yes, that's true. Yes.
But this is not a theorem.
Well, I would like to just comment that in computational complexity, we often say that lifting is a theorem stating a correspondence between two measures. So I think from a background of computational complexity, this is called a lifting theorem. It's completely fine. But probably from information science or information theory, lifting refer to a mathematical correspondence between two.
Usually we don't use that word, but anyway, you need to clearly write down the definition P and SP.
Okay, so I suggest now it's time. So I suggest to move to the next.
Oh, okay, but somehow presentation is very misleading. So you did not explain the correspondence for some formulation, because sample complexity and query complexity is completely different concept. You give some correspondence, P and SP.
Okay, so
Okay, thank you very much.
So because you did not explain the definition before stating the result.
okay, so let's thanks Kuisheng. Okay, so now it's time. So I suggest to move directly to the next talk. The next talk will be an online talk, I think. Yes. So could you please share your slides?
Okay, can you see my slides now?
Yes, I can see. Yes, perfect.
Okay.
Can put.
So, okay. So today I'm going to talk about the exponential hardness of optimization in variational quantum algorithms. And this talk is based on the joint work with Hockey John. Sorry.
So we are waiting. So we don't see the slide in full screen.
Oh, you can't see the slides?
No, I can see it, but when you, I think you are sharing them full screen, and here it doesn't show full screen.
Okay.
You can wait a few seconds. Okay, so now it's perfect. So I will just introduce your talk. So the next speaker is Gang Liu, and the title of the talk is Exponential Hardness of Optimization in Variational Quantum Algorithms. Okay, please start.
Yeah, okay. Thank you. So I'm going to talk about the exponential hardness of optimization in variational quantum algorithms. And this talk is based on this work with Haokai Zhang, Chengkai Zhu, and Xin Wang. And this is the outline of this talk. And in the first part, I will give a brief introduction of variational quantum algorithm and the Baron-Plato's phenomenon. And in the second part, I will talk about main theorem and its implication. And at last, I will give a short summary. So before I introduce our results, we need to know what is variational quantum algorithm and what is Baron-Plato's. So a variational quantum algorithm, which in short is VQA, is a hybrid quantum classical computation framework. And it is specifically designed for near-term quantum devices and has become one of the most promising approach to achieve quantum advantage with NISQ devices. And generally speaking, VQA adopt a parameterized quantum circuit and use a classical computer to optimize the parameters and to minimize the cost function. And in such a parameterized quantum circuit, the rotation angles are uncertain parameters, and the goal to train this quantum circuit is to find the desired circuit parameters. The cost function could be various depending on different tasks and is typically chosen as the expectation value of some Hermitian operators. And take variational quantum algorithm XOR as example, we could optimize the parameters of quantum circuit and to find the circuits that correspond to the ground state of a given Hamiltonian. And this diagram illustrates the scheme of the VQA. So we usually initialize circuit with an input state, and then we run and measure the circuit to get the cost value, and we send this value to the classical optimizer and keep update this circuit parameters. We will keep doing these steps until the parameters are converged, and at last we will get the desired circuit. However, it's not that easy to use variational quantum algorithms, and they're facing a huge challenge called Baron-Plato's. The Baron-Plato is a quantum analogous of vanishing gradients in classical neural networks. It means the gradients of parameters in the random initialized quantum circuit will vanish exponentially with the number of qubits. And the randomness is originated from the random initialization of parameters. And we can intuitively understand this phenomenon if we stand on a very large flat plateau. So, and then we make a step towards no matter which direction we choose, it seems that it is not helpful to find a way to the valley. And with a chipset inequality, this phenomenon indicates that the probability to get non-zero gradients is exponentially small, and thus this phenomenon seriously restricts the practical use of VQA to larger systems, since it will need exponential precision on quantum measurement to make progress on the optimization procedure. And we know that quantum advantage relies only for a large number of qubits, so VQA will not have any quantum speed up if we cannot solve this problem. And why there is a Baron-Plato's? This phenomenon is intuitively from the concentration of matter from HAR. And we know that operations in quantum computing are described by unitary matrix, and we can perform operation on element of unitary group such as apply function to them or integral over the unitary group. So when we do such tasks, we need HAR matter to properly weight the unitary group. Unfortunately, the HAR matter suffers from the phenomenon of concentration of a measure. So Levis lemma tells us how likely is that a function on the group is a specific distance away from the mean value. And in our context, this means that the mean of gradient is 0 over our reachable space. And the Macklin's work, his theorem tells us that we do not need it reach the hard distribution, and two design is enough for the barren plateaus. The two design here is a special case for the unitary T design, which can be regarded as the approximation of hard distribution. And it means that for an example of unitary V, the average of a polynomial of at most degree T over this example V, we have the same result as averaging over the unitary group with respect to the hard measure. So in brief, the example is to design if it matches hard up to the second moment. And as exact to design is integrable using formula, we can get an exact value of variance of the gradients as shown in this formula. And we can see that there is a 2 to the power of 3n here. So this quantity is obvious. It belongs to the big O of the 2 to the minus n and is exponentially small. And here we give an example circuit showing barren plateaus, and the circuit looks like the live diagram, and the parameterized rotation gates are randomly choosing from the XYZ poly gates, and the parameters are random initialized. Then we can see that the variance of gradients will vanish exponentially as shown in this similar plot. And we note here that this kind of repeat layer answers are to design when the number of layer is large. And it's natural to ask how to avoid this phenomenon. So can we use a shallower circuit so that it can will not be a two design? However, we also want sufficient expressibility of these answers because we need it can access to the solution space. Or can we use other optimization methods, or can we have other reparameterization or clever initialization? These methods are unknown, and we need more information to guide us. As we have just said, the barren plateaus means the vanishing gradients, and the calculating gradients is not that elegant, and it does not reveal the problem's essence. So in our paper, we reinterpreted this trainability problem from another perspective. The gradients only reflect the characteristic of the vicinity of the given point. However, we would like to research the whole variation range of the cost function, so which is a difference between the maximum and the minimum value of cost function with respect to the changing a local fixed local unitary. So suppose the whole system has n qubits, and we only focus on its subsystem A, which has m qubits, and remaining subsystem B has n minus m qubits. So look at this figure. So we only focusing on changing the local unitary on subsystem A, and the V1 and V2 here are given circuits. And we gave the formal definition of variation range here, and it intuitively reflects the maximal possible influence that the local unitary UA can have on the cost function. And considering the fact that we usually use single qubit gates and 2 qubit gates, the idea of focusing on local unitary is quite natural. And in this paper, we theoretically proved that variation range is also exponentially small with respect to the number of qubits. And this means that changing local unitary has almost no impact on the cost function. And we illustrate this result in this figure. When we try to optimize a local unitary within a circuit, we will find that it does not change anything regarding the value of the cost function. and we cannot proceed with the optimization process. And the rigorous theorem is present here. So if either V1 or V2 or both form UN2 designs, then we have the following inequality. The expectation of the variation range will be exponentially small. And we notice here that there is a exponential term here. And this WH denotes the spectral width of H, which is the difference between the maximum eigenvalue and the minimum eigenvalue. And combining with the non-negativity and boundedness, we can get that the variance is also exponentially small. And using Markov inequality, we know that a probability of getting a non-zero variation range is also exponentially small. And here I will give a sketch proof of our theorem. So firstly, we will reduce our situation to the traceless Hermitian H, since the identity term here serves as a trivial term in the cost function. And then we will reduce to only consider the maximum term because the bound for minimization term could also be obtained by replacing the H with minus H. And then suppose we want H2 design, we want to find an upper bound for the expectation, this expectation value. And to achieve this, we expand the traceless Hermitian to H in terms of the polystrings on subsystem A. And the first term only acts on subsystem A non-triviality, and the second term only acts on subsystem B non-triviality. And the third term act on both systems non-trivially. And we bound this value by taking the maximization and expectation for each term respectively and add them together at last. For each term, we will use Holder inequality to extract the UA out and bound the remaining part with a specific calculation of two design integral. And at last, we can arrive at our theorem. And if V2 is to design, we can use similar steps to get the result. And then I would like to show some concrete case of application of our theorem. The first application is variational quantum XOR, and it's one of the most famous VQA with the goal to prepare the ground state of given Hamiltonian. For most physical model with local interactions, the spectral width is proportional to the system size. Hence, using our theorem, the variation range vanishes exponentially, and we conduct numerical simulations for the variation range of the VQE cost function using the Heisenberg model. And we can see that when the V1 or V2 is to design, the expectation value of the variation range will exponentially small and less than our upper bound. And the second case is a quantum encoder, which is approach for quantum data compression. And we can also get a similar result, and the expectation of variation range will also have a exponentially small scaling and less than our derived bound. And the third case is quantum state learning. In this case, we derive a tighter bound and demanded randomness become weaker. Here, we only require one design for random circuit, and the experimental results are shown in this figure. And here we have a tighter scaling for this case. And so what implication and inspiration can this result take to us? So most importantly, it reproduces the trainability issue beyond the barren plateaus. So our work can unify the restriction of gradient-based and gradient-free naturally, and the result is independent with the optimizer as well as the parameterization. Our proof has nothing to do with how theta enters the gate. And our work concentrate on the whole unitary. So it is useless to replace an RY gate with usury gate when encountering bait P. And our theorem also present a more tighter bound for the state learning case. So fidelity is a poor choice for random circuit training. And our result can also serve as the guidance for designing wider strategies of solving trainability issue. Some attempts have been made on focusing on gradient-free methods or gate-by-gate optimization or reparameterization. However, our work indicates that these approaches are ineffective in solving trainability issue, and the hopeful strategies may exist in the clever initialization, design architectures, or some adaptive methods. And at last, I will give a brief summary. So in this talk, I introduce Baron-Plato's phenomenon and present our theorem considering the variation range, which is also exponentially small. And we present our application of our theorem on 3 cases. And it's our theorem reinterpreted this trainability issue and can serve as guidance for better strategies to solve this problem. And in the future, I think it's worth exploring the potential solutions of this trainability issue in order to make VQA practical use. And it's also worth research to how to go beyond the local optimization. For example, using sharing parameters like the QAOA. So how to optimize the circuit globally is also worth exploring in the future research. And that's all for my talk. Thank you.
So thank you very much.
Questions?
So I have a question. So you had a few graphs with so yes, this slide maybe with from 0 to 9 qubit or something similar. And
Yes.
how do you get these graphs? Are you doing numerical experiments, numerical calculations?
Yes, we conduct numerical simulations. As is wrong with our laptops.
Okay, so are you using some kind of simulator for quantum system, or do you do?
Yes, actually we use the Paddle Quantum, which is the quantum machine learning platform, and it's quite similar to the Qiskit.
Okay. And is it possible to do similar experiments using a real quantum computer, because you are using only a small number of qubits? So this may be possible, at least in theory.
I think it's quite hard to use a real quantum computer to simulate because it may take hours, and this time will have a great effect on the real quantum devices. And actually calculating the gradients is not that easy in real quantum devices, because we will need, for example, we'll need parameter shift rule, so we'll need much more short. So we'll run this circuit many times, and I think the result is not very precise.
Okay, thank you.
Thank you.
Any, yes.
So I have a question. So please back to your formulation part.
Which part? Sorry.
Formulation. So you use
formulation.
some third page. No, previous one. Previous. Yes, this one. So there's a cost. So the cost given as CH use something, for example. So VQA cost function. So in this scenario, you apply circuit. You input some quantum state and you apply circuit. Then you get the output. Okay.
Okay.
So in that case, you get output and then you can calculate cost.
Yes. So we just run the circuit and measure the circuit and use this data to calculate this expectation value.
So then why this is possible? How do you calculate CH rho U by using quantum circuit, real quantum circuit? You consider some ensemble of input states, not a single quantum state. So you give the some ensemble of quantum states. So then that ensemble is subject to law, and then you can take Hamiltonian average. So then you can get some output. But only a single copy case, you cannot calculate. Or you have some random variable, and that average should be CH rho U, I think.
So sorry, could you repeat your questions?
How to calculate this cost function?
How to
How to
calculate
get this cost function? Because now initially in the one round you have some input state law and you have some that gate and you get output and you can get some outcome. But you use that you get cost function, value of cost function CH rho U. But I cannot find how to calculate this one.
in this cost function, H and
Yes,
rho
yes. How to calculate? So this is not
H and-
real quantum computation. Only some virtual. Only you have some artificially by using a classical computer. Of course, you can calculate this one. But I don't know how to calculate this one in real quantum computer. In real, that kind of quantum circuit. Now you are considering real quantum circuit, okay? Not not classical computer. Of course, if you have a classical computer, then you can calculate trace H rho U dagger. So then this is possible by using somehow MATLAB brackets. Using a MATLAB, you can calculate this cost function, of course. But I'm considering this is quantum information. Then you mean that you should apply some quantum circuit.
Yes, the circuit is we use the parameterized quantum circuit, and the H and rho are given here, so we know the observables. And
How to calculate? How to get this one? Using the real quantum circuit.
So you mean how to get this expected value?
Yes.
I think it's just measure the circuit and use the outcome of the measurement, and we can calculate the expectation.
No, impossible. Only one copy case is impossible. You cannot calculate the expectation. Only you have some random variable. That's average. That's average should be that's expectation. But you have some random variable. This one is not equal to the expectation in the real quantum system.
And so, for example, using swap test, you can calculate the fidelity, and I think it's quite similar.
I think so. I don't know how to calculate fidelity in the real case. Of course, if you have some MATLAB and using the MATLAB package, you can calculate that quantity. But by using a real quantum circuit, you cannot calculate that thing. Not so easy.
Okay, so I think it's time. So maybe we can stop here and move to the next talk. So let's thank the speaker again.
Okay, thank you.
This is Kotaro. Can I comment something? So maybe in realistic systems, you just repeat the experiment many times by fix the same input, I guess. Then calculate cost function. That's what happens in real quantum device.
Okay, thanks for the comment.
But in the case of fidelity, more difficult.
Sorry, could you say again?
In the case of fidelity, that problem is not so easy. In the case of that average, somehow can be given by using the repetition. But in the case of fidelity, not so easy.
Oh, yeah. I'm not sure about the fidelity, but expectation. But
Expectation, but repetition is required. I cannot hear. What happened? Hello?
Can you hear me?
Yes, yes.
Thank you.
Okay, so now we had a small problem with connection, but everything is solved now. So we will start the last talk of this afternoon session. So the speaker is Kotaro Kato, and he will talk about exact and local compression of quantum bipartite states.
Thank you for introduction, and I want to thank the organizers for inviting me to this conference. So today I will talk about some quantum information theoretical problem entitled as exact and local compression of quantum bipartite states. So this is a part of my ongoing work, and I hopefully this will appear in archive soon, like in this month. But yeah, I hope it does. Anyway. So let's start from very basic protocol, which is quantum data compression. So as you may know already, data compression is a very fundamental information processing task. And the goal is sending some message through some quantum channels. So first consider some message, hi, and then we encode the message into a set of ensemble of pure states labeled by the message. And then the task is sending this message by, using these quantum systems. So to do so, we consider average state corresponding to the ensemble and with its purification psi RA. And then this is asymptotic task, which means we consider many IID copies of the purified states. And then what we want to do is performing some CPTP map epsilon here to the accessible state system A. And then what we want to do is compress the quantum system to much smaller system W, and then send it to some other person, like Bob. And then what Bob do is decode the received quantum system states by decoding map D here. And then the goal is, recover the original input state. And the task is send the same message as, but still minimize the dimension of the quantum system which we are sending under this constraint, which means message can be reliably, dated out. And the celebrated theorem of quantum noiseless channel coding, we know that the asymptotically optimal dimension of W, such W under this constraint with asymptotically vanishing errors is given by the well-known von Neumann entropy of the ensemble states, rho A. So because this is such a fundamental protocol, we know that there are lots of some variants of the data compression task. For example, the one variant is, the data compression with one shot, which means there is no asymptotic copy, but we have only one copy. And then if we recover the state exactly, which means this output state is exactly equivalent to the original pure state, and then we know that the dimension W must be equivalent to the rank of reduced state or rho A ensemble state, which means there is no non-trivial compression. We only are able to just, we can only delete, trivial Hilbert spaces. So we cannot non-trivial compress. And in approximate case, the problem become much interesting, and there are a bunch of literature. So this can be viewed as a part of some quantum marginal problem, quantum merging problem for merging protocol or in one shot case, and also, it is also related to rate distortion theorem, blah, blah. But I don't go to much details of this approximate case. So another interesting variant here we consider is when the state on RA is mixed state, not pure state. In this case, it is also, studied what kind of W we can compress. And it is known that the optimal dimension of W is given by the so-called Kowashi-Imoto decomposition introduced by Kowashi and Imoto in 2002, which is for a given quantum bipartite state, rho RA, which can be arbitrarily mixed bipartite states. There always exists some kind of decomposition. I will explain the details later, such that the state is decomposed in this way. And thanks to this decomposition, we can calculate the asymptotically optimal size of the dimension W, which is given by this one, and it could be smaller than the von Neumann entropy. So if we change this part from pure state to mixed state, then we could compress much more compared to the original Schumacher compression. And this is originally proven by Kowashi and Imoto when R is restricted to classical system in 2001, and recently this is extended to quantum systems by these two people. So what is Kawashimoto decomposition? So is again the decomposition of a quantum bipartite state. So we have a bipartite state rho RA such that rho A is full rank. This means we can restrict, we can always restrict the Hilbert space on A to be the support of rho A. So this is just, without loss of generality, we can assume this. And then what they said is there exists some decomposition of the Hilbert space on A in this way, direct sum of factorized Hilbert spaces, such that again, this bipartite state is decomposed in this way. And this decomposition satisfies nice property against every CPTP map, completely positive and trace preserving map on A, which preserves the bipartite space state. And this, if the CPTP map satisfies this state, this property, then the corresponding Stein-Spring unitary can be decomposed in this way. But this part is not so relevant in this talk, so just forget about it. And what is important is we can always decompose any bipartite state in this way. And the left-hand side part of the decomposition represents the quantum correlation between R and A. And omega part only, have a classical correlation with this with R. So in this way, we can decompose the correlation between R and A into quantum part and classical part somehow. Okay, then we are going to move the main problem discussed in this talk, which is one-shot and exact compression of mixed quantum states. So this is combination of previous two variants of original quantum data compression protocol. So what we consider is mixed quantum source. We have a rho RA between A and R. And then we are going to send this system A through some encoding channel to some, another party like Bob, and then Bob decode the received state to some another output state. And we declare that this protocol is exact, means that the output state is exactly equivalent to the input mixed state as a whole. Why we would consider this, I talk about this motivation of this protocol later. But anyway, now we are just focusing, this kind of protocol. And the question is how much W can, how much can we compress the system W? I mean, in other way, what is the minimum dimension of HW here? So actually, we already knew the asymptotic result, and also one can easily check that the minimum achievable compression in this one-shot exact case is also given by Kawashimoto decomposition. It's such a powerful tool. So if we have a Kawashimoto decomposition, then Hilbert space can be decomposed. We said Hilbert space on A can be decomposed in this way always. And then what we can show is that HW, the minimum, this is the minimum achievable dimension of this variable compression given by the sum of Hilbert spaces of the only left-hand side, which is quantumly correlated to R. So, okay, so the problem is already solved, but the true problem here is, however, how to calculate this dimension of these, Kawashimoto decompositions. In the original paper, actually, there is an algorithm is shown to calculate the Kawashimoto decomposition. However, the algorithm, actually, the purpose of the algorithm is obtaining the full decomposition of the Hilbert spaces with certain bases. So it is too much detailed, and what we want to know is only dimension of this sum of Hilbert spaces, but not structure of those explicit decomposition. So it is actually too much, and the algorithm itself is hard to implement. So it is too complicated. So we want to simplify them, and we only want to know that information about that dimension. So now the sketch of our main result is the following. So let's consider any bipartite state, and without loss of generality, we restrict rho A is full rank. Then we developed a way to calculate some pure state on, pure state, 4-bipartite pure state, which belongs to 4 A's, and those A's are all, have the same dimension. So it is just a copy of A's, such that this 4-bipartite multipartite pure state contains the information of the dimension. So we can calculate the dimension of the minimum achievable compression by calculating the rank of the reduced state of this pure state. I'll explain how to construct this pure state. This calculation of pure state C tilde requires some optimization process, which may cost computational resources. So we also found bounds which are easier to calculate. So there is another matrix C, which is before optimized C tilde. And we show that this rank of C, this is not vector, this is matrix. And this matrix contains information of the W already in some sense. So this HW dimension HW is sum of dimension HILs, but rank of this C is sum of square of those dimensions. There is slight difference, but it's enough to bound this desired optimal dimension. So these are main results. This calculation of this second part requires exact diagonalization of dA square times the dA square matrices, which is C. So it is not that efficient, but I guess this in general, this kind of calculation of one-shot quantity is not so easy, so it will be okay. Just in case I comment about classical case, what happened in classical case. So suppose rho RA is some classical state, and then there exists a decomposition. And of course, this state does not contain any quantum correlation. So the dimension of each factor, HAIL, is one-dimensional in this case. Then one can show that the non-trivial compression, so the dimension of HW can be smaller than the trivial rank of the reduced state, if and only if there exists two random variables such that satisfying this condition for any R. So this means A and A prime have the same, exactly same conditional probability distribution. Then one can obtain non-trivial compression. This is, for example, if we have a trivial case is when R and A is independent, then whatever you perform on A, it is always guaranteed to be the safe compression. And the other slightly non-trivial case is when R and A1 and A2 forms a Markov chain, and then we can, for example, if A2 is independent from A1 by conditioning R, then we can always discard A2. So we can always compress A1, A2 to be A1 only. But we can check these conditions also satisfy this condition. So this decomposition is again in classical statics known as Fisher-Neyman factorization. So it is at least consistent with classical case. Okay, let's move to the method. The behind the proof is the so-called minimal sufficient subalgebra, which sounds kind of scary, but anyway, it is pretty useful. So we declare that the output state of the protocol is exactly equivalent to the input mixed state. And this condition is known to be equivalent to the following by this paper. So there exists a set of state A's. Some positive operator on MR, and then trace out R state on M. And then the original condition for states on M is equivalent to the but this must hold for arbitrary states on this set. And then thanks to the result by Anna Yenchova, Dennis Petz, we can show the coercive mode decomposition of bipartite state is originated in actually the so-called minimum sufficient subalgebra generated from this set of states, which is defined in this way, but the detailed structure is not important. However, I would like to comment that the result obtained in this work is strongly relying on the recent development, not so recent, but development by Anna Yenchova. So the originally Petz introduced this algebra, which is just a multiplication of two unitaries, but Anna Yenchova shows that this algebra is actually equivalent to this kind of algebra, and this difference actually matters. But anyway, this is just the details. And what we would like to know is that the left-hand side, dimension of the left-hand side of coercive mode decomposition. And actually, the point is that the left-hand side is corresponding to the factorization of this minimum sufficient subalgebra defined in this way. So our strategy to calculate the dimension is focusing on this subalgebra, or actually the commutant of the subalgebra. So commutant is, of algebra is a set of operators which commute with every element of the algebra. So this forms another, again, this forms another algebra and can be decomposed in this way. This is well known in, operator algebra. But nice thing is this commutant also has the information about the left-hand side Hilbert space as an identity part. And then we consider the so-called conditional expectation, which is a CPTP map defined in this way. This CPTP map acts as some kind of projection, linear map version of a projection onto subalgebra. So we know projection onto subspace, but this is a projection onto subalgebra in some sense. And the strategy is, our strategy is first obtain the choice state of this conditional expectation, CPTP map, on this commutant of the minimal sufficient algebra. And then from the choice state, we can extract information of the desired dimensions. So to get the information of the choice state, we first characterize the subalgebra in other ways. To do so, we introduce Petz recovery map. This is pretty recently, attracting many people in quantum information. But it is defined in this way. For any CPTP map and the state sigma, we define Petz recovery map as is in this way. And then we introduce similar definitions, which is kind of complicated. But anyway, this is necessary to explain my result. So we first define some operator JRA from given bipartite state. So everything, the point is everything is constructed from just given bipartite state. We start from a raw array. Then we first construct JRA, which is just, modified, slightly modified from the original bipartite state. Then we know that this JRA is also a positive semi-definite operator, and also partial trace on R is identity on A, which means JRA is a Choi matrix of some CP unitar map from R to A. This is Choi-Yamilkovsky isomorphism between operator and map. So if we have this CP unitar map from this operator, defined in this way. And then we consider the dual, Hilbert-Schmidt dual of this unital map, which is omega AR. This is CPTP map now. And then further consider complementary channel, which is, we first consider Stein-Spring dilation of CPTP map and then trace out the output, original output Hilbert space. This is how to get complementary channel. But at the end, we get some CPTP map from A to environment system E. And then Pets recovery map appears. So when we consider complementary channel constructed from the given bipartite state and the Pets recovery map with respect to this omega and completely mixed state. And combining these two, we get some map from A to A finally. And then let's fix T as a fixed point algebra of this CPTP map, which is actually CP unital map as well. And what we show is that the commutant of the minimal sufficient subalgebra, which we try to characterize, is actually the largest subalgebra of fixed point algebra of this guy. That is invariant and this so-called modular operator for any time. Well, it is still complicated, but I don't go into explain the detail of the proof, but why this kind of weird map appears, because, first, the minimal sufficient subalgebra is generated by, modular operator transformation plus this operator in the middle. And this operator, by using these definitions, can be viewed as the output of this CP unital map. This is the point. Then XA belongs to the commutant of the minimal sufficient subalgebra, means that XA commute with every generator of the minimal sufficient subalgebra. So this means this. And this helps a lot to prove this lemma. Actually, we need to use another, quantum error correction techniques. But anyway, this is the essential point why this weird omega appears, and also Pets recovery map. So now we have this characterization of the some algebra, and we would like to construct the Choi matrix of the conditional expectation from this lemma. So to do so, we first focus on first look these CPTP maps P, and actually this is delta is not CP. This is CPTP. So tau T and delta as not maps but operators on acting on operator space. So T is linear map from A to A. So we look this map as a super operator which acts on which is a matrix on acting on A tensor A1, and A1 is just copy of A. And we just decompose it in this usual spectral decomposition. And we also, so this ET can characterize this fixed point subalgebra. So we also want to characterize this modular operator in terms of super operator, which is given by this RLA. So this guy is a generator of the delta rho T. So, we have two operators characterizing one and these two, constraints. So from this matrix representation, fixed point algebra is just, given by support of P1, and also, invariance under this action is given by this kind of restriction. So we find that this subalgebra is corresponding to this V operator subspace, actually. So now we have a operator subspace characterization of the subalgebra which we want to characterize. And conditional expectation is actually the projection onto that subalgebra. So we want to obtain the projection onto this operator subspace, which is given in this form. So this PV is a projector or a super operator projection, and which is a super operator representation of the conditional expectation, which we want to obtain. And we want to get choice state of the conditional expectation. And it is well known that super operator and the choice state of conditional expectation defined in this way is related via the so-called reshuffling of matrix, which is in this way. So this is just relabeling the order of the indices of this PV. Then we get choice state from this super operator. So finally, so from the original state, bipartite state, we get some map, and then we get this super operators constructed from state, and then we get this projection, and then by reshuffling, we finally get the choice state. And then the second step is obtaining the information of the dimension from the choice state. So the choice state of conditional expectation on the commutant looks like this, where tau is completely mixed state and psi I is maximally entangled state. And pi is just a probability distribution determined from the dimension ratios. And it is easy to see that the rank of C is defined, determined just by this completely mixed part, which is actually Hilbert space of AIL. So this is what we want to calculate, right? Dimension HAIL, the sum of these guys. However, because we have a completely mixed state, sorry for the noise. We have the completely mixed states on both sides. We don't have the true HW, but the, square sum of these HAILs, because A1 is just a copy of A. So these two guys matches. So we have this. And also, what we want to know is this guy, dimension HW, which is, written this way. So we want to this, but we have this now. However, this is enough to, in some sense, because we can bound the dimension HW by, by looking at these relations. So in this way, we can have the bounds of both upper and lower bounds of the desired dimension. This is first part of the result. And then how to get the not squared sum from the choice state. Then we need some optimization, unfortunately, so far. So from given choice state, we first purify the choice state in this way. So this is so-called canonical purification. So there are a bunch of, infinitely many possible purification of mixed state, but we choose particular purification, so-called canonical purification. So graphically, this is just, reflected as a mirror. So, we, given in this way. So we just apply this operator, the choice state, to some one side of maximally entangled state, then we get this purification. The problem here is, there is some correlation between the purified case here, and we want to, this part forbids us to obtain the true dimension, not squared sum. So we want to get rid of this entanglement, actually. So we just apply some unitary here to minimize the entanglement between left-hand side and right-hand side to get this kind of state. So this state is now, we don't have an entanglement here. And only this difference systems only correlated to the desired, Hilbert spaces. So by taking the dimension, but to obtain the information of the dimension of those L guys, we just need to calculate the rank of these subsystems. And this optimization can be performed by some gradient algorithm given by this paper, for example. And the result is, if we calculate the rank of reduced state on this side or this this side equivalently, then we get the optimal dimension of the compression. That is the main result of my work. Okay. So in the rest of the talk, I would like to explain the motivation. I put this in, the second half because this is more like physical and not so quantum information theoretic. But anyway, so why we are considering this problem? It is actually related to tensor networks. So tensor networks is a way to represent some tensors into small bunch of tensors. For example, let's consider some many-body quantum state and represent this in some computational basis or product basis. Then we have a coefficient Ci1 to Cin here. And the principle of tensor networks is representing these coefficients, not vectors, coefficients into some networks of tensors. And there are a bunch of choice of networks, and then there are a bunch of various applications in quantum many-body physics. I skipped this part because the essential part is not so relevant. And one of the well-known, well-studied tensor network states is matrix product state. So tensor network state is a quantum state which whose coefficients can be represented by tensor networks. That's the definition of tensor network states. So matrix product states, then coefficients can be represented by some product of matrices and then taking place. So graphically, this is represented as in this way. So this is just a subclass of all the possible quantum states, only tiny, subcorner of Hilbert space, but it is pretty relevant in quantum physics. And nice thing is the number of parameters needed to specify one MPS is much, much smaller than one needs to explain the full generic quantum states. And also, there are nice relation with entanglement, but it doesn't matter. What I want to explain is there is so-called nice renormalization flow of MPS. So MPS has a physically applicable coarse graining operation. So if we have a MPS, a part of MPS on two sides, then simple matrix algebra guarantees that there exists isometry, which is actually given by just a polar decomposition of tensor. Isometry such that the two tensor is mapped to one tensor, smaller tensor. So the information contained in these two outer, horizontal legs, vertical legs, just compressed in this tiny single leg by just using isometry. And by repeating this procedure many times, then we can achieve some fixed point. And this fixed point is has pretty simple structure. So we can, reveal lots of physical property. We can prove it. For example, relation to quantum phases. So it's pretty useful. However, besides, aside of this one-dimensional pure state case, still lots of things are open in tensor network theory. For example, here we show the other tensor network states called matrix product density operators. So instead of one leg open legs in MPS, we have two legs corresponding Buller and Ket. This is a 1D generalization of matrix product state, which is pure state to 1D mixed states. And this is actually a good answer for thermal states in 1D systems. And it has also nice relation to general 1D thermal states, analytically proven. And of course, because we saw, MPS has a renormalization procedure and flow, so we want to consider renormalization process for MPDOs as well. And actually, Sirac and others introduces that kind of concept for MPDOs. So in the case of MPS, we had considered isometries, but in the case of MPDOs, then we have to consider CPTP maps instead. Then the fixed point is defined as tensor network states, which each tensor can be, doubled by CPTP map and coarse-grained by CPTP map, and this, process is exact because it is in fixed point. This is the definition. Then, if the tensor satisfies this condition, then this Slack and others show that this fixed point tensor network states have a very beautiful structure, which means state is actually nearest neighbor commuting parent Hamiltonian, a given state of nearest neighbor commuting Hamiltonian. So, we want to have a denormalization flow, and if we can repeat this and go to fixed point, then we have this nice, characterization theorem. But the problem is, it is unclear if there is a denormalization flow which achieves this fixed point. They didn't mention about it anyway. So we need to establish, renormalization flow for MPDOs and, unlike RG flow for MPS, which is isometry, one needs to apply CPTP map. So that's why, we considered this, the previous, data processing problem. So what we want to do is, applying some operator and applying some operation to tensors for MPDOs operators, and then decompose the tensor into relevant part and irrelevant part, and then just discard irrelevant part to get rid of some entropy. And the structure is pretty similar to Kawashimoto decomposition, and one can easily see that if such a denormalization process exists, then it must follow the Kawashimoto decomposition. So the left hand, quantumly correlated part is relevant part, and omega part classically correlated to R part is, the one can discard this part, and then repeat this, and we can coarse grain, the 1D mixed state. So the remaining question is, if one can, for any matrix density, product density operators, starting from matrix product density operators, if one can always find some CPTP map, which has constant size index. If one cannot compress, then there is no RG flow for MPDOs achieving the previous introduced fixed point. So this is still open problem. I'm still performing numerical tests, but unfortunately here I haven't obtained some, result which I can show here. But anyway, because we have a nice bounds already, so we can at least numerically characterize calculate the growth of this minimum possible B tilde from given quantum states. And now, we just decompose the 1D state into 2 parts, and then it is just quantum bipartite states. Okay, so that's all for my talk. So in summary, we have studied one-shot and exact data compression of mixed quantum stores. So this is another new variant of quantum data compression. And we have obtained at least one way to calculate the minimum achievable dimension. It is exponential, but still, one can perform within, some computer if, the dimension is not too large. And the future direction is, as I said, the problem is originated in tensor network. So I want to investigate it more. And also from quantum information perspective, there are a bunch of ways to generalize this. For example, of course, here we will consider exact compression, but we can ask about approximate scenario. And also, more sophisticated algorithm is desired. And also it will be interesting to see any entropic relation to entropic quantities, for example, conditional one-shot F divergences or something like that. That's all for my talk. Thank you very much.
Thank you very much. Any questions? Either from the audience or online. So the one you mentioned about the approximate scenario looks like a very natural open question. So
yes,
what are your expectations?
So at least we can consider smoothing the quantity we defined. So we have an exact case, and so we can just for given state we just consider epsilon ball around it, and then optimize over those epsilon ball and calculate exact compression dimension over epsilon balls, and then taking minimum. we can define in that way, but there are could be in various different definitions, and also there are some problem. It is also related to, for example, information bottleneck problem. Something similar is discussed, but so the generalization is not unique. So I'm not sure which direction is good, but it will be definitely interesting.
Okay, thank you. Any other question? Yes.
Yeah, thank you for the talk. This is a naive question. So when you have an MPS, then you
Would
have,
you show your name?
sorry, this is Chris Bourne from Nagoya. When you have an MPS, you have good control over, for example, its entanglement entropy, and you have, you can understand these quantities well. When you have what these are MPDs or MPDOs, can you, is there any sort of analogous results about entropy or relative entropy or entanglement entropy that?
Yeah, there is an area law for MPDOs as well, but not entanglement entropy, because entropy, behaves like volume law for mixed state, thermal state. But instead, we have an area law for mutual information. So, for MPDOs, the mutual information between A and B, written in this way here, is bounded from the above by bond dimension. So this is just analogous.
Thank you.
So and also that's why we expect this, minimum dimension B tilde is also, constant, independent of the size of B, because mutual information is always constant.
Any other questions? Maybe online? Okay, then, so it's time. So let's thank the speaker again.
Thank you very much.
And this is the end of today's afternoon session and today's all sessions. So is there any message from the organizers?